Hi, everyone. We're going to discuss today the binomial distribution. I'm Carolyn Chapel, and it is one of a very useful, very commonly used, very often used distribution. It is a discrete situation, so we will be looking at a discrete probability distribution, and kind of we can think about it. So I want you to imagine if you were to flip a coin 40 times. So over and over and over and over and over and over and over again. And what we're going to do is we're going to let X be the number of heads. That we get in those 40 flips. And we would maybe want to know, what is our probability distribution look like? So I'm just going to I'm not actually going to do this, but we'll kind of just talk through it a little bit. So X, which is the number of heads, since we're flipping it 40 times, could be 0, 1, 2, 3, 4, 5, all the way up until we get 38, 39, and 40. So we have 41 different possibilities, 0, 1, 2, all the way to 40. Now, to calculate our probability, we would need to know what this sample space looks like. And you could list them. You could create a tree. But since we're completing this coin flip 40 times, that task is daunting. So luckily for us, we don't have to do that, because this situation is what we call a binomial. Okay, and how can I tell if something is a binomial? Well, there's some criteria that a binomial follows. Okay, and for it to happen, all 4 of these criteria have to happen. So the first criteria is that the experiment, or what you're doing, is performed a fixed number of times. Okay, so for our case, this fixed number of times is the number of times we're going to flip this coin. So for our example, we have 40. Okay, we sometimes want to call this not necessarily the number of times, or maybe it's the number of trials that we have. So we have a finite number of trials. Okay, the second thing that has to happen is each trial, or each time we do this thing, is independent. And to remember that what we mean by independent is what happens on one attempt is not going to affect what happens the second time. So if I get a head on the first flip, that's not going to affect if I get a head or a tail the second flip. So that is going to mean that they are independent. Some things in the past we've talked about being dependent is maybe drawing a card from a deck where we do not put that card back in. If we were to put the card back in, then it's independent. But keeping that card out, so without replacement, a lot of times is going to be dependent. The third case, or the third criteria that has to happen, is each trial has 2 outcomes. Okay. Now, sometimes it's not necessarily 2 outcomes, but we can reduce it to 2 outcomes. Can't spell today, sorry. All right, so we have 2 outcomes. And this one is a good example of 2 outcomes because we get a head or a tail. A lot of times we will refer to those outcomes as a success or a failure. Okay, and the last thing that has to happen is the probability of success remains the same for each trial. Okay. And some people would argue, well, if it's independent, then of course that happens. There are some very limited examples of where you have independence, but the success or the probability does not change, or vice versa. It's where they do remain the same, but they're not independent. Okay, but they are so rare that we're not going to discuss them in these videos. So some things to kind of think about, or just looking at a few, flipping our coin, some examples. And we'll look at to see, are they a binomial? Are they not a binomial? So as we've been saying already, flipping a coin 40 times. Yes, it's a binomial. Okay. What if I did shooting a free throw? 7 times. This is where you can start to do some arguing about getting in the groove kind of thing. But for mathematical speaking or statistical speaking, we're going to say that, yes, this is a binomial. When in reality, it may not necessarily be that, because each trial may not be dependent or independent. What happened on your first shot may affect what happens the second time you shoot a free throw, because we're human. Okay. Another one that I had mentioned is we're going to draw 4 cards from a deck. Of cards without replacement. That's what this is, a no. Okay, because they're not independent. What happens the first time will affect what happens the second time, and those probabilities do not remain the same. Okay, some people might argue that we don't have 2 outcomes. However, you can think of it, depends on what you're looking for. You could say, I'm looking to see if we have a heart or not. So if we reduced it down to the 2, getting a heart versus not getting a heart, getting a numbered card versus not getting a numbered card, we could consider this possibly those 2 trials. So if we put it back in there, then that would become a yes. If we were looking at something, getting a heart, not getting a heart. Another example, roll a die until a 3 is rolled. Okay. Well, rolling a die and you're looking for a 3 could be considered each trial is independent. You could think of it as it has 2. Probability of success is the same, 1 out of the 6. However, since we don't know when we stop, this is not going to be a binomial, because we continue this experiment until that 3 is rolled. So sometimes we'll get that 3 on the first one. Sometimes it may take us 100 rolls to get that 3. So, but this is a different situation, and there is a probability distribution out there that takes care of that. It's not something that I cover in the course that I'm making these videos for, but it is out there. Okay, so once we know that this is a binomial, since it does happen quite often, we do have a formula for calculating probabilities of each of these. So if I wanted to list all 40 of them out and put their corresponding probabilities in there, I could do that. So here comes our formula and some of the notation. So you find the probability of a binomial distribution. Okay, so we have probability that x, which is our random variable, is equal to some x, one of the little outcomes, one of our possible outcomes. Okay, the formula is as follows. We have an n factorial. Don't worry, I will explain what n and all these things mean. We have n minus x, this x being this x, and we will do some examples so that will help solidify these pieces, x factorial. Then we're going to multiply this by x power and 1 minus to the n minus x. Okay. Some of you may recognize this piece from previous lectures or previous notes. That is your NCX, so the number of ways and things choosing x of them at a time. So we could write this as p to the x times 1 minus p n minus x. All right, so let's do an example. I'm not going to use our 40 just because the numbers are a little big, but let's flip a coin 7 times. Oops. Before I do that, I better let you know what n and p and all those things stand for. N is the number of fixed trials. Fixed trials. And P is going to be the probability of success. Okay, and again, X is going to be the outcome or the number of times that it happens. We get those successes. The number of successes are concerned about. Okay, so let's do an example. I will create another video with more examples, which also go into how to use some of the technology that we have out there. But for this one, I'm just going to do a brief introduction so we can kind of get a feeling for what's going on. So let's flip our coin. Let's flip a coin 7 times. Okay, and I want to know what is the probability that we had 4 heads. Okay. So flipping a coin 7 times, what is the probability that we had 4 heads? So 4 heads, 3 tails in some order. Okay. Flipping a coin is a binomial because we have a set number of trials. We're only doing it 7 times. We have 2 outcomes, a head or a tail, head being our success in this problem, tail being our failure. They are independent from one another and the probability does not change. So the probability of getting a head every time is a half. All right, so in my notation, I'm kind of looking for what is the probability that X is 4. So if I were filling out the probability distribution, let me go back here, this guy, underneath the number 4, this is what I'm calculating. I'm calculating that probability that would match underneath the 4 if we were doing it 7 times, not 40. Okay, so I like to kind of write all the pieces, so I kind of have them all ready for me. I already have the 4 here, but I also want to know n, which is the number of fixed trials. That's how many times we're doing this thing. That is 7. And our p is going to be the probability of a success. Success being we get ahead, so that would be our 1/2. Or if you want to, 0.5 if you don't like fractions. Okay. All right, so I'm going to put the pieces in here. So my n is 7. And I'm kind of doing it longhand for those of you that like to do all the math. 7 minus 4 factorial, 4 factorial. We will have our 1/2, or I'll put 0.5 to the x, which is 4. My 1 minus 0.5 is this 7 minus 4. I'm going to clean this up a little bit. 7 factorial, 3 factorial times 4 factorial. These are multiplied down here. 0.5 to the 4th, and we'll also have a 0.5 to the 3rd. Okay. For those of you that want to use the buttons on your calculator, this is 7C4. So 7 combination 4. Going to the calculator, so make sure you can do this on your calculator using being multiplication going on here. You should get the number 0.1640625. Okay, so try it, double check, make sure you get there. If you need to, stop the video and check it out. Did you get there? Fabulous. If not, keep trying. You should get there. Oh, no, you won't, because I changed my problem. Boy, did I just screw this video up. That's okay. I'm human. So I will quick figure it out here. Let's try 0.273437.5. That looks a little better. Okay, let's go a different example. And I won't change it from the one in my notes so that I can write down the right answer. So let's do something a little bit more complicated than flipping a coin, but not too complicated yet. Let's roll a die. 12 times. And what we're going to do is we're going to let x be the number of times we see a 4. Okay. And I want to know is, what is the probability that we saw 3 4s in these 12 rolls? Okay. Right. So I'm going to again write down the little pieces that I have. My n, that is the number of fixed trials that I have. So the number of fixed trials I have here is 12, because we do this, roll this die 12 times. My p, the probability of a success in this problem is getting that 4, and probability we get a 4 is 1 out of 6. If you change this to a decimal, you will have some round off error, so it is just best to use the 1/6 if you're doing it using a calculator. As I said previously, I will create another video using technology so you can see how technology can help us. And if you want to think of it, we were looking for the probability that x is equal to 3. So 3 of those 4 rolls. So we're looking for the probability that x is equal to 3. And I'm going to use the combination form because many calculators nowadays do have that button on there. So it is a 12C3 times our P, which is 1/6, to our X value. And then we're going to do 1 minus the 1/6 to our 12 minus 3. So again, 12C3. And if you're kind of wondering where these pieces come from, okay, this 12C3 is kind of finding the number of ways you can order H's, or I should say 4 and not 4, number of ways you can do that. It's because there's 12 slots, and we're going to choose 3 of those slots to put a 4. And then we have the probability of each of those pieces. Well, the probability of getting that 4 for those slots is that 1/6, where the probability for all the other slots is 5/6. So if you're thinking of a tree almost, and you were looking down a line that went 4, 4, 4, not 4, not 4, not 4, not 4, you'd have a 1/6, 1/6, 1/6, and the rest would be 5/6. And we'd have this many branches that would contain 3 of those 4s. Okay, so we have a 12C3, 1/6 to the 3rd, and 5/6 to the 9th. It can come out very clear. There we go. And now if you actually do this number here is 220, just kind of double checking. And our final result is 0.197396. Okay, hopefully you can get those results. Again, I apologize for making the error previously, but I am human. I'm not perfect, nor are my videos, but hopefully they help explain things a little more. I'll see you in another video where I do some more examples using technology to help us get the results.